I'm curious to hear your presentation, your audience.
All right, well, thank you, Dr. Fromm. And hello, everyone, and thank you again for joining my presentation today on securing the DevSecOps environment, approaches, methods, and tools. Again, my name is Aarlen Baker, and I'm a principal security architect at Wind River within our technology office. Our presentation today will focus mainly on providing a summary of which security features are required to secure a DevSecOps environment. We'll also cover the usage of the distributed, immutable, and ephemeral, or DIE principles, as these principles can further strengthen the security posture of the environment. And we will finish with how we approach third-party penetration testing for a DevSecOps environment and how this compares to a traditional static development environment. But before we get into our presentation, I wanted to cover a couple of definitions to ensure common understanding. Cloud native development. So the on-demand availability of computer system resources, specifically processing and data storage. It's the scalability of resources that's an important attribute of the cloud native environment, and then one that we can take advantage of for our DevSecOps environment. The other definition for containers, that's the mechanism to package applications and its dependencies in a standardized manner. And of course, our DevSecOps environment is comprised of many of these containers. And then finally, Kubernetes, that's the orchestrator of our containers that includes the deployment, scaling, and the management of those containers. Kubernetes can tear down a container from one cloud resource and spin it back up on another cloud resource, and we can take advantage of that. So the recent supply chain attack is telling us that we as developers, as we shift security left in our development processes, our adversaries are following right along with us. So by entering the vendor's development environment, the attackers were able to insert their malicious code into the binary that was later deployed to unsuspecting customers, both commercial and government. And because the attack vector was part of the binary that was digitally signed, it gave the illusion that the binary was indeed authentic. Now, this type of attack highlights the need to make sure our DevSecOps environment is a secure DevSecOps environment. So to help identify the need for the defensive layers, we can do a security assessment of the environment to identify the security features to add. Now, there are many different approaches in determining threats to a system, including many of what you've heard, such as Stride or Pasta, Octave, and several other approaches. But regardless of which security assessment approach you use, the end result is that we get a list of what the assets are, what the threats or vulnerabilities to those assets are, and then which security implementations are needed to protect the identified assets from the identified threats. And one last item, no security is perfect, so we have to make sure that we have a list of security-related events identified in case any forensics are needed to occur or any indications of compromise need to be determined. Another input into the security assessment is the list of related specifications to be compliant with. Now, here's a summary of many NIST and US DoD specifications and guides to take into consideration when securing a DevSecOps environment. Now, while all of these are important, several here are referenced in my presentation, including the key management publication from NIST. This is a 3-volume set that provides a very comprehensive description of key management and the guidance around key management. Of course, the security and privacy controls from NIST, the NIST 853. And then the Committee on National Security Systems Policy, or CNSSP 15, which talks about the use of public standards for secure information sharing. And then, of course, the Zero Trust Architecture specification to move from static defenses to focus on users, assets, and resources within our system. Now, in security, there are always discussions about cryptographic algorithms and their associated key sizes in which to use. Now, the measure of the level of effort required to break these algorithms and key sizes is called security strength. And security strength is defined as the number associated with the amount of work that is required to break that cryptographic algorithm. And this number is represented in bits. So if we intersect CNSSP 15 along with the NIST key management standard, we find that 128 bits is acceptable, but this comes with a very large asterisk next to it, because these estimates will be significantly impacted, of course, when quantum computing becomes practical. But after we do that intersection, we can realize that we can use SHA-3 256 message digest and RSA 4096 digital signatures to achieve the recommended security strength of 128 bits. So from the US DoD's reference design document, here's a typical DevSecOps environment block diagram. Starting from left to right, the diagram shows the user interface as the IDE, and then the different repositories with separation between the development and the release repositories. And I want to highlight the important flow of data from the development environment through the test and integration environments, and finally to the released repository. Now, it needs to be highlighted the importance of the flow from left to right through the various components of the DevSecOps environment. Notice the data diode-like flow and the sequence of the flow through the components. Now, we can leverage modern cloud-native technologies in the development of our DevSecOps environment, remembering that cloud-native gives us that ability to run scalable applications in both a public cloud, our own private cloud, or a hybrid cloud environment. And this is a significant advantage in ensuring that the inclusion of security principles keep pace with the application development, especially in a continuous integration and continuous delivery model. Now, taking that black diagram, we can determine the list of the assets within the DevSecOps environment. So of course, the repositories themselves, where the code, the libraries, and the resulting artifacts reside. And then the build tools and the test tools, and very importantly, their configuration. Now, remember a few months back, it was announced that a static analysis tool was not getting configured properly, and the default credentials were left configured, allowing attackers easy access into the development systems. So this highlights that the configuration of these tools must be taken into consideration. And then connectivity. We must know which component is talking to which other component within the environment. Now, as the diagram shows, the development environment can talk to the test environment. However, the development environment should never communicate directly with the release repository, because it must go through the test and integration environments first. So we must take connectivity into consideration and ensure that it's enforced. And then, of course, persistent storage in a cloud environment. We always have to make sure that that's encrypted to protect any critical data, such as intellectual property. And then, as I mentioned, as part of our security assessment effort, the security event logs are an absolute mandatory requirement, but also we have to remember that event logs are a goldmine of information for an attacker, because it not only shows what's being logged, but it also tells them what's not being logged. So we have to protect the confidentiality of these logged events as well. So now that we have the assets, we need to determine the threats or vulnerabilities against those assets. And so we can do that by taking the definition of information security to help determine those threats. So the term information security means protecting those assets or that information from the unauthorized actions that I have listed across the table. So unauthorized access, use, disclosure, and so on. And as we go through our list of assets against these unauthorized actions, this is where we want to apply security features to mitigate the threats. Now, you'll notice that on a particular column, the modification column is checked against all of our assets. Again, going back to that recent supply chain attack, it showed how the vendor's development environment was changed to incorporate their malicious code. So we must ensure that our defensive layers defend against these unauthorized modifications of the components within our DevSecOps environment. Now, from our security assessment matrix, we can determine a list of technologies and the capability of each technology that will be used in securing our DevSecOps environment. Now, this diagram shows the specific technologies and the capabilities of each technology that we can leverage in securing our environment. So let's start at the foundation of our pyramid as we cover the technologies. The hardware security module is considered effectively our root of trust for our DevSecOps environment. Now, the HSM is a purpose-built FIPS 140 Level 3 certified appliance that we use for all cryptographic functions within our DevSecOps environment. Now, because of the criticality of this device, both physical and network access to the HSM is tightly controlled and always requiring a two-person authorization for any changes. The private certificate authority is important for a fully on-premise configuration. We have several customers where they're going to be wanting to set up a DevSecOps environment in a full on-prem configuration. And so in this case, they will not have the ability to reach out over the internet to access the standard public certificate authorities. So we must make sure that we have certificate revocation services implemented and available to our DevSecOps environment. Now, our key hierarchy here is a bit of an eye chart, but we want to make sure that we have a certificate chain in place that minimizes potential impact in the event of a compromise. Also, we want to have a hierarchy that supports the frequent certificate rotation within our DevSecOps environment. Now, the functions required in a DevSecOps environment drive our key hierarchy to include generation of the intermediate key pair for the Istio service mesh, and this is what enables mutually authenticated TLS communication between our components. We need to have a key pair for our web interface specific for the on-prem configuration only. Now, remembering these types of configurations can't reach out to the public certificate authority, so we need to take that into account. We need to have a key pair for ensuring the integrity of the artifacts as they reside in the release repository. So once the build pipeline completes and the build artifacts are in the release repo, we need to make absolutely sure to be able to cryptographically verify that those release artifacts do not change. And then we need to have key pairs for specific communication within our DevSecOps environment that fall outside of the Istio service mesh. And remembering our keys are RSA 4096 with either SHA-3 256 or SHA-3 84 as supported by our DevSecOps components to ensure we meet the security strength of 128 bits. Now, identity management is critical not just for people accounts, but also service accounts. So service accounts provide the identity for processes that run within our DevSecOps environment. And so what our pyramid here is representing is all the users within an organization. And this shows as the privilege level increases, hopefully the number of users within with higher level privilege decreases. So starting at the foundation of the pyramid, to gain access into the corporate network is, of course, the standard corporate ID credentials and probably a corporate VPN set of credentials. Now, the next layer is to access the DevSecOps environment itself, and this needs to require a separate set of VPN credentials, different from the corporate VPN. And this level of access is for the majority of our DevSecOps environment users. The next level is that of elevated users for our DevSecOps components. Now, these users require the same VPN credentials as mentioned for the DevSecOps users, but now adds an additional layer of multi-factor authentication to gain access to those elevated commands. So multi-factor authentication could include FIDO2 keys or the time-based one-time password applications. And then finally at the top, and hopefully the smallest number of users, we get into the privileged access function that requires a two-person access control. So privileged access management, or PAM, is the approach where no one person in the organization has the root password. In fact, we want to get to a point to where the password to the privileged user account is not known by anyone, but rather is provided by tooling based on an authority to continue type model. And so getting to a two-person rule helps mitigate against compromised identities and credentials within our DevSecOps environment. Now, a typical DevSecOps environment, again, contains many different components, okay? And of course, those components all require communication to achieve the value of the build pipeline. However, we must make sure that all communications are not just encrypted, but also authenticated and authorized. We can only allow communications between specific pairs of components within the DevSecOps environment. And so this is where the Istio service mesh can be leveraged for this. Now, this diagram is from the Istio documentation page on security. And this shows an overview of the components and the usage of Istio. Notice how Istio provides a proxy or a sidecar in front of each service. And it's this proxy that provides the mutually authenticated TLS connection and, of course, the important logging of each connection as it occurs. And then you'll notice at the top of the slide, we only want a small subset of cipher suites. We want to support perfect forward secrecy and maintain a protected communication throughout the DevSecOps environment. So these cipher suites are listed on the OWASP cheat sheet for the recommended ciphers to use within a TLS environment. Now again, DevSecOps is all about the practice of shifting security left in the development process. But we need to build our DevSecOps environment to align to these same principles, okay? So again, all CVEs need to be patched in all of our components. As I stated, there's a large number of components all working together in our environment. We need to make sure they're all current and they're all patched. So that means we need to have a very strong vulnerability management process in place to ensure all these components are patched and current. And then the containers themselves, we need to make sure that they are secured. We don't want to have any hard-coded secrets in any of the containers. Definitely no root privilege allowed. And one item to strive for in the container is getting to the point where the container does not change its configuration at runtime. We want to get the container to a point of an immutable state, if at all possible, because if it does change, we can detect that and determine if we're under attack or not. And then remember my comments about proper configuration of the components. Again, we can use OpenSCAP tooling to ensure our security technical implementation guide configuration is correctly applied to our applicable DevSecOps components. And of course, don't forget about the host machines themselves. The BIOS and the host OS must also be actively managed because that's our foundation. All components in the DevSecOps environments have to generate security-related events. Now, no question, this is going to be a large number of events to manage, and it's going to require tuning over time as we use our DevSecOps environment. But a technology that needs to be used is a Security Information and Event Manager, or SIEM, to be able to quickly process these events and determine the appropriate response. And as I said, the protection of these security events is critical. The log files can tell a hacker a wealth of information on not just what is being monitored, but what is not being monitored. And then also, we have to take into consideration the archival time of these logs. Industry compliance, such as the United States HIPAA regulations, can span many years. And this archival process requires an integrity seal or a digital signature over the logs to ensure no modifications have occurred while they've been archived. Now, this diagram is from the NIST 800-207 publication on Zero Trust Architecture, specifically Figure 2 of that publication. Now, what we did is we annotated the diagram around the outside, mapping our technologies that we covered to the individual Zero Trust Architecture components. So starting in the upper left-hand corner of the diagram and then going around counterclockwise. The CDM system, that's the continuous diagnostic and mitigation system. So that's our vulnerability management capability. The next component is the industry compliance. Remember my slide up front, listing out the various specifications that we need to take into consideration and be compliant with. Our threat intelligence feed is another part of our vulnerability management process. So we know we have a current intelligence on the different threats that are occurring in the wild. Our activity logs are our security event logs from all of our components within our DevSecOps environment. Now, the data plane and control plane components for the policy engine, the policy administrator, and the policy enforcement point, that leverages a combination of the technologies, a virtual private network, our Istio service mesh, identity management, and privileged access management all come together to implement those critical components of a zero trust architecture. And then, of course, our SIM used to process the security events, identity management for the ID management, again, for both people accounts and service accounts. Our public key infrastructure, we implement that with a combination of our hardware security module and our private certificate authority. And then the final component of the data access policy, again, is using Istio and privileged access management. So all of these technologies work together to enable a zero trust architecture. Now, I brought up vulnerability management here several times, and I wanted to break this down. And again, as mentioned, we need to do more than just CVE scanning and mitigation. Yes, no question, that's absolutely critical. But we need to make sure that we have an accurate catalog of all the components in the DevSecOps environment. Again, there's tens, hundreds of components running within an environment like that. So we need to be able to go through the repositories, the log files, and make sure we have an accurate identification of all the components running within our system. We don't want to have a mismatch, because then we're going to go off and waste time tracking down CVEs for something that we don't really have in our system. And the threat intelligence feed helps keep us current, again, on the threats impacting the components within our environment. So again, all these activities work together and forming a solid vulnerability management capability in support of our DevSecOps environment. And the DIE principles. So I attended a presentation where these principles were explained. So the distributed, again, our inherent cloud native implementation lends itself nicely in being distributed for both an on-premise and in the cloud or hybrid configuration. Immutable, going back to my statement made about containers, we don't want to have any configuration updates at runtime. We want to be able to detect a configuration change, and if there is a change that's required, then we can have the container torn down, the updated container in our registry is in access and pulled, and then relaunched by Kubernetes. And ephemeral, and this is a critical piece to the DIE principles. We want to get to a point of a short lifespan of the containers running in our DevSecOps environment. So when the system is designed to use ephemerality, it enables the following. It simplifies the distribution of any updates to our secrets. So if an update's required, the system will consume that updated secret as part of its normal operation without any manual intervention. The short-lived certificates for MTLS is in the same category. Now, we can never remove revocation services, but our reliance on revocation and key compromise mitigation can be reduced. The deployment of the CVE patch containers, again, happens as part of the normal operation of the system because our containers are short-lived, and so it's easy to push out an updated container when necessary. And then most importantly, a container that has a short lifespan is going to frustrate the hacker, because if they do gain access to our container, it'll be torn down in a short period, respun up in another cloud resource, and the hacker's got to start all over again. And finally, penetration testing. Now, again, the cloud-native DevSecOps environment gives us a specific advantage over a static development environment. In this case, we're able to create a completely new and separate instance of our environment within our cloud service provider, completely removing the concern from the pen test team of crashing a production system. Now, with this approach, we're going to support 4 different levels of pen test access. So, of course, first is no access. This would mirror what an attacker from the outside could perform. And then the second would be a standard user, so what a malicious insider could do to our system. The elevated user, so the privilege escalation used in our second tier of functions within our environment. And then finally, the privileged user. Now, again, this isn't just root access, but rather to ensure our privileged access management was correctly implemented, verifying access to one component of the environment doesn't enable access to another component of the environment. And then as a specific control in NIST 853 mentions, pen testing is a specialized type of assessment conducted on information systems to identify vulnerabilities that could be exploited by adversaries. So by having an external vendor that specializes in vulnerability discovery provides an enormous value to ensure the security of our DevSecOps environment. And so in conclusion, as security testing becomes incorporated into the development lifecycle, it's of paramount importance that the development environment itself be secured. We covered several technologies and capabilities of those technologies using the foundation in securing our DevSecOps environment and the application of the DIE principles to extend the security posture of our environment. And then finally, leveraging third-party penetration testing vendors to provide security evaluation of our environment. And with that, I thank you, and I turn it back to Dr. Fromm.
All right. Thank you very much, Mr. Baker, for this very impressive demonstration of how complex things actually can come in this very open DevOps world. I think it's like a little bit in the real world. On the one hand side, we want to have a certain flexibility, but this obviously also attracts hackers who might actually violate and really do some nasty things we definitely don't want to have. So I'm looking forward on also discussing that a little bit deeper in the Q&A session coming up. Okay. So the next presentation which will come, we're going to shift a little bit to the model-driven development topic there. But before that, as usual, a short break so that we can set everything up. But please do stay tuned and use the Slido link also to get in some questions for the Q&A block. Thank you very much.